Hello class. Today we're going to go through our example of using root locus from start to finish and how we might run a control problem. So I'm working from the example located on Canvas, so please download the root locus 2-tank example. It starts off with giving the values of the two tanks, so we have capacitance of C1 and C2, R1 and R2, and I'm going to just plug in those values so we can just look at the full transfer function. But question 1 says, look at our open loop function. So these are the two tanks before we've added any sort of controller. And the question asks, what is the corresponding Q out for a given input of Q in? So if we look at this system, we can see that if we want to put something into the format of A omega n squared s squared plus 2 zeta omega ns plus omega n squared, we can see that for the example problem, A is equal to 1, since we have 1 over 400 in the omega n squared term when we standardize our system by dividing by that 4,000, and we have 1 over 400 in the numerator of our function. So A is equal to 1, which means that Q out will equal Q in. So whatever our flow is that we put into it after we've reached steady state, we should approach that our Q out will equal to our Q in. Now, our second question is the response fast or slow? So what we need to do to find that is we want to find the poles of our system. So the poles for G of S, while it might be tempting to say that 7 over 40 is equal to 2 zeta omega n, this may not be an underdamped system, so we should use our quadratic equation to find our poles, and we find out that S is going to be equal to either 0.0157 if we round, and 0.159. And so looking at our simplification of a second order system when it's overdamped, we can see that this will act like a first order system that has a tau equal to 63 seconds. So that would be 1 over the pole closest to our imaginary axis, which would be that first pole. And that would give us a tau of 63.7 seconds, so it'll take roughly 3 minutes for our system to reach steady state. So in fluids that might be seen as enough, we're going to say that that's a fairly slow response. And we are given the tasks that we want our settling time to be within 30 seconds. So we would like TS, and I'm going to say it's for 5%, to be equal to 30 seconds. And we would like our MP to be equal to 16.5%. So for this, underdamped second order systems are typically much faster than an overdamped second order system. And it's going to be easier for us to create this by simply using an underdamped second order system form. So if we do that, we're going to say that 3 zeta omega n should be equal to, or, because that'll be our settling time, or less than 30 seconds. We will say that our percent overshoot, which is going to be the exponential of negative pi zeta over 1 minus zeta squared, should be less than or equal to 16.5%. And let's do 100% over here. And let's make that a little bit more legible. I'll just do a little e to give us some space. So with these criteria, the task just tells us to develop a feedback controller. Step 1 is going to be finding our pole locations, and we'll do that by saying what our zeta would need to be. So we have that zeta omega n must be greater than or equal to, so we'll take those, that 30, multiply by that zeta omega n, which is why they're on the different sides of the equality, then have 3 divided by 30, so they all have to be greater than or equal to 0.1. Meanwhile, for our percent overshoot, if we go backwards, we're going to find that zeta has to be greater than or equal to 0.5. And we're going to start off by saying our desired pole location will be when zeta is equal to 0.5, omega n is equal to, if zeta is 0.5, omega n would have to be 0.2, which would give us poles at negative 0.1 plus or minus our plus or minus 0.1732J. So we get that just by plugging in the zeta and omega n terms that we get to have those pole locations. We found our pole location, and now we want to do 2b. Use root locus to determine if we can use a proportional controller. So we have two options. One would be to just put in our open loop system to a root locus, in which case MATLAB would generate a root locus that, since we have two real poles, they would meet in the middle. And when we look at that, we see that they meet at somewhere before 0.1. And because they meet somewhere before 0.1, using that root locus of MATLAB, we can see that we will never be able to have a zeta omega n of 0.1 or greater, because when we have a pole located somewhere here that's not at 0.1, we'll have another pole that is closer to the origin, causing our tau to be too slow. So the fastest that our system can respond in terms of settling time will be when it's underdamped, but we see that with a proportional controller it's not going to be enough. If we want to do this manually using the angle criterion, we can do so by saying that we want to check our location. So we have that desired of -1 plus or minus 0.17. So we want to see the angle of G when S is equal to -0.1 plus 0.1732 J. And I'm ignoring the minus because if we draw one point, we know that there'll be a point on the opposite side of our real axis. So we can draw some poles, some vectors that start at our open loop pole location, go to our desired closed loop pole location, and we can find the angle θ1 and θ2 just by looking at the distance between the two poles. So we can say that this angle criterion is going to be equal to -θ1 minus θ2 because they start at our poles and go to our desired closed loop pole location, which means that we will treat them as negative. If they started from 0, we would treat them as positive. So we can say that θ2 is going to be equal to, and we can do an arctan of the rise. So the rise is going to be 0.1732 divided by, and we will have, this is a 0.1 here, 0.1 minus, or we can just do the higher number first because we're considering absolute distance. So it'll be 0.159 minus 0.1. And θ1, you could do it a couple different ways. I usually like to just do 180, and we want to make sure that your calculator's in degrees. But we'll do 180 minus, and then here we'll have our arctan of the same rise, 0.1732, divided by, and for now we have that this will be 0.1 minus our 0.0157. And I'm rounding a little bit, which is why it's important to check your numbers at the end and make sure you ended up with a decent controller. especially if you do have to round a little bit. And if in doing so, we should get that our g of s, our angle of g of s, is equal to negative 115.9 degrees for theta 1 minus 71.1 degrees for theta 2, which does not equal 180 2n plus 1. We would need to add a 0 in order to cause this to work, and if we do so, we would no longer have a proportional controller. We'd have a PD controller. So the answer to 2b is that no, a proportional controller does not work. So we can find that either using that angle criterion or using the root locus plot to see that there was no way that we could have reached it at all. So now we'd like to design a PD controller. So we have negative 187 degrees for our open loop angle criterion, trying to achieve that desired pole location at negative 1 plus or minus 0.1732J. And we saw that we can't do it with a proportional controller, but we can if we add a 0. And so what we would like is we'd like to have the angle of our controller combined with our open source system to be equal to some phi, which will be caused by adding a 0, minus theta 1 minus theta 2, which will be equal to phi minus 187 degrees. So that tells us that we would want phi to be equal to 7 degrees. And since phi needs to equal 7 degrees, that's going to say that if we have 7 degrees here, we're going to have 0.1732 for our rise. So what we need to do is we need to use trigonometry to solve for x, and then add 0.1 to our answer because we have that it's located at negative 0.1. So we should get that our z is located at negative 1.51. And in doing so, we can now visualize our system. We could either plug it into MATLAB, where we now have an added z, so that our new open loop system, and we can just do GCGO to remind ourselves that we have a open loop version, is going to be s plus 1.51 over our original system. And so we could either write it in terms of the simplified version or the non-simplified version. I'll just keep it with the non-simplified version because either one is fine. And MATLAB can deal with the algebra on its own. So we could plug this into our root locus, and MATLAB will give us a root locus that looks something like this. And so we'd have one pole that goes to our 0 and another pole that goes to negative infinity. And we can either find our exact point by using the magnitude criterion if we wanted, or we could just click on a point on our root locus and just find something that would work. So we could click on it and find when k is equal to 10, that we would have a pole at negative 1 plus 0.174i. And that would give us the properties that we would need. So that would be how we would go through a PD controller design from start to finish.